All right, today we're going on a little journey. We're going to take a word you and I use every single day, difference, and unpack it. Because it turns out it's so much more than simple subtraction. It's actually a key that unlocks some of the most profound and, honestly, beautiful ideas in all of mathematics.
So let me ask you something, and it's going to sound almost ridiculously simple. What's the difference between two numbers? Seriously, take a second. What's the very first thing that pops into your head?
Yeah, I'm willing to bet you landed right here. The difference is just what you get when you subtract the smaller number from the bigger one. 5 minus 3 is 2. It's simple, it's straightforward, it's elementary school stuff. And look, you're not wrong, but that is just the tip of the iceberg.
Because what if we flip our thinking on this? What if difference isn't the final answer? What if it's actually a tool? You know, an engine for generating new things, like patterns. This is where the story really gets interesting.
So let's build on that basic idea and see just how much bigger this concept really is. We're going way beyond simple subtraction.
A great place to start is with something called an arithmetic sequence. In these, we have what's called the common difference, usually written as just d. Now, this isn't a one-and-done subtraction. Oh, no. This is a constant, a repeating rule that tells you exactly how to build the next step in the pattern.
And check out how it works. To get from 1 to 6 to 11, you just keep adding 5 every single time. To go down from 10 to 8 to 6, you're just adding a negative number, minus 2. It even works with fractions. That constant difference, it's literally the DNA of the entire sequence.
So right there, that's a huge shift in thinking, right? The difference is no longer some static result you write down on a page. It's become this dynamic engine, a creative force that can generate a whole predictable pattern, seemingly out of thin air.
Now, if it can do all that with a simple string of numbers, what happens when we take this idea into the world of algebra?
Well, that's where the patterns it creates get even more elegant.
Ah, a true classic, the difference of two squares. You've probably seen this formula before. It's this incredible little shortcut that says if you take a squared number and subtract another squared number, it always factors out into their sum times their difference. It just pops up everywhere.
But you don't have to just take the formula's word for it. We can actually see why this works. Just picture this in your head. You've got a big square with an area of a squared. Now, we're going to slice a smaller square, b squared, right out of the corner. What you're left with is this L-shaped area, which is, a squared minus b squared.
Okay, now for the clever part. Watch this little bit of mathematical magic. We take that L shape and we make one simple cut. We take that smaller piece, we swing it around, and we slot it right next to the bigger one. And bam! Look at what we have. It's a perfect new rectangle. The total area is exactly the same, but now its sides are a plus b and a minus b. It's a perfect visual proof. How cool is that?
So difference can build patterns and give us these amazing shortcuts in algebra. That's pretty cool, but what if it could do something even more powerful? What if it could help us describe change itself?
All right, this is where we take the biggest leap of all. Let's leave behind the neat and tidy world of straight lines and perfect squares. Let's talk about curves, things that are constantly changing, constantly in motion. What happens when we apply our idea of difference here?
This leads us to something that sounds a little intimidating, the difference quotient. But don't worry, the idea is actually pretty simple. It's like finding your average speed on a road trip. You take the total distance and divide by the total time. It gives you the average change. But calculus? Oh, calculus is way more ambitious. It doesn't want the average speed. It wants to know your speed at the exact instant you glance down at your speedometer. That's the derivative.
So that's what the derivative is all about. It expresses that instantaneous rate of change. The big question, though, is how on earth do you measure something at a single frozen instant in time?
Let's go back to our curve. We start by just picking two different points. Then we draw a straight line connecting them. That line is called the secant line, and its slope is just the average rate of change between those two spots. It's our difference quotient in picture form.
But here's the brilliant part. What if we start sliding those 2 points closer together, and closer still, until the difference between them is practically zero? Watch what happens to that line. It pivots, it shifts, until it's just kissing the curve at one single point. It becomes a tangent line. And the slope of that line? That's it. That's the derivative. That's the instantaneous rate of change.
And what's amazing is that this core idea, using difference to understand the world, it doesn't stop with calculus. I mean, calculus is a huge deal, but this concept is so fundamental, it shows up all over the place in other advanced fields too.
Take set theory, for example. There's something called the symmetric difference. It sounds complex, but just think of it like this. You have your list of favorite movies, and I have mine. The symmetric difference is all the movies that are on your list or on my list, but, and this is key, not the ones we both love. It's the stuff that makes our tastes unique from each other.
And you see this everywhere. There's percentage difference for comparing values when you don't have a single correct answer. There's the symmetric difference we just saw for comparing entire collections. In every single case, it's the same fundamental idea, just wearing a different hat. Measuring a gap, making a comparison, finding the difference.
So let's just pause for a second and look back at how far we've come. It's kind of wild when you think about it. And it all started with that one super simple question.
I mean, seriously, think about it. We started with 5 minus 3 equals 2. That basic idea evolved into a blueprint for creating entire patterns. Then it transformed into a slick shortcut in algebra. And then, in this mind-bending twist, we shrunk the difference down to nothing, and it became the very heart of calculus itself. We even saw it used to compare completely abstract groups of things.
So if there's one thing to take away from all this, it's that the simple, humble idea of difference, of just asking, what's the space between these two things, is one of the most powerful keys we have. It unlocks our understanding of patterns, of structure, and even of the very nature of change itself.
And that kind of leaves you wondering, doesn't it? If a concept this basic, this everyday, is packed with so much hidden power and beauty, what other simple ideas are we all taking for granted? What other secrets are just hiding in plain sight, waiting for us to look a little closer?